Welcome back to ECE 320A. We are in Unit 10, and that means we're doing Bode plots, which are covered in Appendix E, and homework number 10 will be due at the end of this unit. We're breaking down the process of sketching straight line approximations for Bode plots, or finding frequency response information for a transfer function. In this video, we're going to look at linear factors. Linear factors now are associated with s raised to the first power, and those can be either numerator or zero factors, or denominator downstairs pole factors. Again, we're just trying to quickly learn strategies for sketching the magnitude as a function, or in dB, as a function of frequency, and phase, the angle, as a function of frequency. We'll have two different plots, and these strategies are all being designed or explained assuming that we have all of our poles and zeros living in the left half of the complex S-plane. All the real parts of the poles and zeros are negative. They're in the left half of the complex plane. Again, we're breaking this sketching process down to where we're looking at the individual factors or terms. We've already looked at the constant term. In this video, we're looking at the linear terms. Once we have all of those put down on the same plot, then we can just slide our thinking and our sketching from the left, small frequencies, to the right, large frequencies, and add up the magnitude components as we transition from low frequency to high frequency, and we can add up the phase component from low frequency to high frequency, adding up those angles, which we've already sketched the component pieces after we learn these different techniques. So let's now look at sketching the linear factors for the Bode plots, and again, it's probably easier to get a handle on this by actually looking at specific examples, and we've already started with a transfer function, so let's now continue with that and assume that we now want to sketch the magnitude and phase as a function of frequency for this zero factor. And this zero factor now we're evaluating, essentially, if you wanted to think about it in a way of connecting with what we've already talked about, now we are evaluating this expression, this factor. We have a zero sitting, and I'm going to exaggerate its location, but let's now say that this is now at minus 0.1. We want to know quickly, as we march up this imaginary axis, here's our j omega axis in the complex S-plane, we want to know, how do these lengths change as omega increases, and how do these angles change as we're looking up that imaginary axis. That's really all we're doing when we draw these sketches, and we want to be able to do that quickly rather than to look at an infinite number of points along this imaginary axis. Can we simply look at a few points and connect some lines and be done with our straight line approximation sketch? That's what we're trying to accomplish. Let's look at the magnitude sketch first. We're now taking the magnitude in dB, so we have 20 log base 10 of the magnitude of this factor, which is j omega over 0.1. Our zero is at 0.1 plus 1. If we look at small frequencies, and small typically is a decade before the break, so we're thinking, oh, a decade before 0.1, we're looking at 0.1 times 0.1, or now we're at 0.01. That anything at 0.01 or smaller in frequency is small, And if we looked at the magnitude of j 0.1 plus 1, we can pretty much neglect the imaginary component and just say, oh, we're looking at log of 1. So we're looking at log of 1. Log of 1 is 0. That's why we can say, oh, we're flat, or we have a magnitude of 0 dB until we actually now are going to make this approximation even exaggerated a little bit. So we're going to slide through that small value, which was 0.01, and go all the way up to the break frequency. That's why it's called the break frequency of 0.1. And at that point, then we will start to say, oh, we now need to consider the frequency effect, or this imaginary component is now starting to contribute to the magnitude piece of this expression, because now we're looking at 1 plus j1, and the magnitude of that is the square root of 2. So let's now start considering this. So now we break at omega equal to 0.1 at the 0 location, and since it's just a single factor, we are now going to be changing as a function of frequency, and we're going to have a slope. Because it's upstairs, because it's a 0 factor, we're actually going to be sloping up at 20 dB per decade. So as we change omega by a decade, which for understanding purposes, a decade is a factor of 10. You've heard of a decade of years. You're 20 or you're 2 decades old, you're 20 or so. An octave actually is a factor of 2. If you looked at frequencies musically, you would see that an octave now consists of a factor of 2. So if you went from middle C, let's say that that's roughly 250 hertz, up to the C above that, you're now talking around 500 hertz. So octave is a factor of 2. When we're dealing with an expanse of a multiple of 10 in frequency, from let's say 1 to 10, or from 2 to 20, or from 50 to 500, now we will experience a change in magnitude of 20 dB. It'll be up for zeros, and it'll be down for poles. If you wanted to examine that change over a smaller interval of frequencies, then a factor of 2 might be helpful, and a factor of 2 is an octave, so 6 dB per octave is equivalent to 20 dB per decade. So if you wanted to look at a shorter length of frequencies from 2 to 4, then we would see or experience 6 dB of change, instead of going from 2 to 20 and experiencing a 20 dB of change. That's what I might be talking about when I say an octave or a decade. That's now what you can start considering. In this case, we want to now sketch that. So now we have two straight lines. We have one that's flat, horizontal at 0 dB, and then we have another one that has a slope to it, and in this case it's a 0 factor, so our slope is up, it's upstairs, and it will be sloping at 20 dB per decade, and that slope will begin at the break frequency. So let's see if we can sketch that. We now are 0 dB until omega equals 0.1. So you might try to just locate 0.1 on your graph, and 0.1 is 10 to the minus 1. We now said that we're flat until that frequency. Now if we go a decade beyond that, and we're sloping at 20 dB per decade, then we should be at 20 dB 1 decade beyond 0.1. Well, 1 decade beyond 0.1 is 1. So now you can just sort of say, oh, we should be there. A decade beyond there, we're a decade further up. So now when we're at 10, we're at 40 dB, and this is now our straight line that we sketch. And if I've labeled this and scaled it properly, at 100, we would be at 60 dB. And that's now the sketch, the straight line sketch of a zero factor where the zero is located at 0.1 or at 10 to the minus 1. That's all there is to that sketch, where this slope is now plus 20 dB per decade. What about the phase? Well, now it helps to actually think about three different points, really a small frequency, a large frequency, and the frequency, Goldilocks frequency, right in the middle, or the just right, that's the break frequency. We know what that is for this particular zero. We're now talking about our omega naught being 0.1 radians per second. The small frequency, omega 1, is now a tenth of omega naught, and the high or the large frequency is a decade above, or 10 omega naught. So this is now our small, this is now our large. So for every linear factor, you can quickly identify these three frequencies: the small, the large, and the just right, which is the frequency itself, or the break frequency itself. Pictorially, if we're thinking about angles, let's just look at what this might provide in terms of insight if we look at this S-plane. Suppose we are sitting on a zero or a pole, but let's just look at zeros for now. Suppose that zero is now at minus omega naught. If we walk up the imaginary axis, again, the frequency response is obtained by evaluating this factor along the imaginary axis. When we are sitting at a small frequency, or anything less than a decade below omega naught, 0.1 times omega naught, then what's the angle of that particular anything less than that? Well, that's pretty tiny, so we're just going to approximate that to be 0. Now, look, I have a gap here because obviously I'm not 10 times omega naught in this sketch. So now crane your neck a little bit more and think about going all the way up to 10 times omega naught. And the limit is going way off to infinity. If you're going way off to infinity, how far are you going to have to crane your neck? Well, now that's going to actually be at an angle of 90 degrees. So when we get to 10 times omega naught, we're just going to say, oh, we're craning as big as we can. So we're just going to say we're craning our neck until 90 degrees. So we're transitioning from 0 degrees to 90 degrees over this 2-decade interval. A decade below the just right frequency or the break frequency, and a decade above the just right frequency. And we can calculate all of those for this particular example. In our case, omega 1 is a decade before omega 0. So now we're a factor of 10. I'm sorry, we're 1/10 of where our break occurs, which is at 0.1. So now we are going to be considering our small frequency to be at a value of 0.01 radian per second. And at that particular frequency, now we have effectively j 0.1 plus 1. Here is our complex number, and we want to know what's the angle of that. Well, effectively that's just 1. We're going to say that that 0.1 is negligible in the vertical direction. So now we have this angle of 1, which is now going to be 0 degrees. That's just, if we looked at the point 1 in the complex plane, we don't have to change our head at all to see anything. So now we're at 0 degrees for small frequencies. For large frequencies, in this case omega sub 2 is 10 times our break frequency of 0.1. Now we are, in this particular example, looking at 1 radian per second. Now we have strained our neck a lot, and so now we're looking at the angle of this complex number that's bigger than an angle of 1 plus J10. Well, now J10 is the dominant piece, so we're just going to say that that's approximately J10's angle, and the angle of J is 90 degrees. So now we want to connect these pieces. We are saying that for small frequencies, 0.01 or less, we are going to have an angle of 0 degrees. For frequencies beyond a decade above the break, we are going to be at 90 degrees. And at the just right frequency, which is omega naught in this case, which is 0.1 or 10 to the minus 1 radians per second, then we're looking at the angle of J1 plus 1, and I hope that you can see that that's now going to be 45 degrees. So it's now 45 degrees, and we need to just connect those dots, and there is our straight line sketch of the phase due to this zero factor. So we're transitioning from 0 degrees to 90 degrees. We're going up to 90 degrees because this is upstairs. This is a zero factor, and this slope is plus 45 degrees per decade, and it's spread just over a 2-decade expanse. After you get through 2 decades, it quits sloping and it flattens out and becomes constant. So unlike the magnitude, where we could simply break at the break frequency and establish that slope for all frequencies thereafter, for the angle, we have to turn it on a decade before the slope, that is. We turn off the slope a decade after the break, and now we have to keep track of both before and after. That's why it's important to think about small, just right, and large frequencies. So if we do that for the linear factor, for the pole, now we're downstairs, now we're bending everything down, but let's just keep in mind what we are working with. If we have now omega naught is 200, small is now a decade or a factor of 0.1 less than that. So now we're looking at small being 20, and large is now 10 times 200, or at 2,000. And in keeping with this, remember what the log of 2 was, base 10? That was 0.3. So now the log of 20 is going to be 30% of the distance between 10 and 100. So this 0.3 gives us a 30%. That's now 2 is, in a logarithmic sense, is 30% of the distance between 1 and 10. So now 20 is actually going to be 30% of the distance between 10 and 100. 2,000 is going to be 30% of the distance between 1,000 and 10,000. What I'm meaning by that is when we start sketching the phase, those fractions of distance between tens and 100s and 1,000s and 10,000s will become important. For now, what do we know about the magnitude? Well, we know for omega less than 200, we're going to be just treating that as flat at 0 dB. And 200 now is bigger than 100. It's less than 1,000. We know that we are going to be somewhere between here, and because 200 is 30% in a logarithmic sense, the distance between 100 and 1,000, now we simply identify 30% of the distance between 100 and 1,000, and this is now our break frequency of 200. So we're coming along at 0 dB, until we reach 200. Then at 2000, which is right there, we'll be 20 dB down from that. At 20,000, which is 30% of the distance between 10,000 and 100,000, will be 20 dB down from there. And now we can simply connect those with a straight line. And I'm straight line challenged, but hopefully you see that this is now minus 20 dB per decade beyond omega equal 200. And that's now the magnitude sketch of this linear factor, where the linear factor is j omega over 200 plus 1. The phase is now, because it's a pole factor, it's down. We will eventually reach minus 90 degrees. And when will we reach that? Well, when we reach a large frequency, which is 2,000. And 2,000 is now 30% of the distance between 1,000 and 10,000. So if we go 30% there, we'll just call this now our minus 2,000 frequency. And we will then be at minus 90 degrees. We're 0 degrees until we get what? A decade before the break. The break is at 200. So this is now, maybe I shouldn't say minus in this case because we're talking frequency. But now we had 200, which is right there. And we're now centered on that. We will be at minus 45 at 200, and at 20, which is 30% of the distance between 10 and 100, this is now considered our small frequency. We're 0 degrees until we reach the small frequency, and then we transition over that 2-decade interval with a slope of minus 45 degrees per decade. Then after 2 decades, we are now down to, again, this is a straight line approximation. We're now at minus 90 degrees. And that's how we can now sketch these linear factors in our Bode plot sketching.